Cloud Service Manager is one of the fancy titles that we give ourselves at CERN. I lead a team of some dev and ops people that actually run OpenStack in production, but it's standing on the shoulders of many other teams that worry about networking and hardware and so on. I'm sorry, I'm nursing a bit of a cold that is turning into a full-blown man flu, so I'll be sneezing for the next 25 minutes through my presentation, so bear with me, please. I will be taking sips occasionally. And to encourage you to ask some questions afterwards, I brought stickers. And not only the old-fashioned square ones, but also super new hexagonal ones, which I'm told are all the rage in for laptops. So there you go. Very good. I should have something to click on. All right. So I'll be talking about what we do at CERN in general, how we do computing at CERN, how OpenStack started to fit into that picture 6 years ago, actually, and what our OpenStack deployment looks like today. I could talk until lunch, but I can only talk until coffee, so at one point somebody will have to stop me. So CERN is the European Organization for Nuclear Research, founded in 1954, just a few years after the Second World War. Located at the border between Switzerland and France, near Geneva. So CERN was created as a safe space, can we say, for scientists from the member states just after the Second World War to work together in a peaceful environment. So working together in a peaceful environment is actually one of our mission statements. We do fundamental research, obviously. We train the next generation of physicists and technicians and engineers. And we've been doing that for some over 60 years now. Initially 12 member states, now it's 22, and you see a very long list there of other countries way beyond Europe that also contribute under various forms. It's a big place. There's about 2,500 people employed by CERN, but at CERN every day there's over 10,000 people. From many of those visitors are coming from about 200 countries worldwide, from different universities and institutes participating in some of the 20 experiments that are being conducted at CERN. So you can imagine it's a very dynamic place. It's a great place to be, actually. So we do about 20 different experiments at CERN, but our flagship project is called the Large Hadron Collider, or the LHC. So it's a proton-proton collider of 27 kilometers in circumference, about 100 meters underground, between the Jura Mountains, which you see on this side of the picture, and the Lake of Geneva, which you see on the other side. I think the Mont Blanc has just been cut off from this picture, but you get a feeling it's a very nice spot for a particle detector. Along that particle beam, there are 4 major experiments. 2 of them, Atlas and CMS, are the big ones. The other ones are not small either. You already see the data rates projected on there because the experiments take data underground, but the data they ship to the computer center, we'll get there in a minute, is actually quite voluminous. If you look very closely on the left-hand side, you also see a cloud. I think that may have been the first cloud that we had to deal with. It's grown. So underground, a shot of the accelerator. You see there's a bend at the end of the tunnel. A small one, of course. It's 27 kilometers in circumference. There's about 2,200 superconducting magnets underground that guide the proton beams and accelerate the particles to within a fraction of the speed of light. There's 2 beam lines, beam pipes, so these beams are kept separately, but they interact at 4 different places where we've built the detectors. This is not a Roman or Gothic cathedral. This is the Atlas detector. If you look carefully, you see an Atlas physicist standing in the front, wearing a CERN hat. Atlas is 46 meters long, 25 meters high, 25 meters wide. So it's huge. It weighs about as much as the Eiffel Tower, I believe. It's also huge in an organizational sense. There's, I have to check this every time. I think it's now about 3,000 people who are working on that collaboration alone. Same is true for the CMS experiment. The Alice and LHCb experiments are smaller, but still getting close to about 1,000 people working on it. So this is why we call this big science. It's not just the size of the experiments, it's also the size of the collaboration. And the Nobel Prize winner Barry Barish, who got this prize last month, was for the gravitational waves discoveries. He was actually a particle physicist, and his contribution to that project was actually to manage large collaborations like the ones we do in high energy physics. Also large is our data volume. So the 4 experiments have produced something like 50 petabytes worth of data on tape. They have produced much more data in the experiments, but most of it gets thrown away by filter farms close to the experiments. And the more interesting events are being sent to the data center, where we keep them on tape. We have about 200 petabytes worth of data on tape, because it's cheaper than disk still, and it also gives our customers a warm, fuzzy feeling that there's actually something tangible where their data is. I find the cost argument more convincing. The second thing we do with that data is we ship it to some 200 sites worldwide that form the LHC computing grid. So, and the CERN is in the middle of that grid, and the second layer, the Tier 1 institutes, there's about 12 of them worldwide. One of them here in the Nordic countries, and then there's about 200 or so institutes that also get either a fraction of the data or produce Monte Carlo events to participate in the analysis of all this data. And then the third thing we do in the computer center is analyze that data itself, of course. The experiments run their analysis programs on the compute farms that we have both in the Geneva data center as well as in the data center in Budapest, 22 milliseconds of latency away. And it's, excuse me. And if all goes well, the outcome of all this is physics. And as you know, everything did go well. In 2012, CERN could announce the discovery of the Higgs boson. And in 2013, the Nobel Prize was awarded for that work. So that's what we do. In numbers, this computer center, it's big as well. So there's 2 data centers, one in Meyrin, which is about near Geneva, and Wigner near Budapest. And I'm not going to read through this, but you see there's tens of thousands of servers, and the amount of data that we store on disk is it still flabbergasts me. This, however, started to point to a problem. About 6-7 years ago, we started to realize that this was more than we could actually deal with in terms of computer hardware. The CERN data center is a building from the early 70s. Computing is older than that, but we were still managing all that infrastructure with some tools that we'd been developing ourselves. And as you can imagine, over time, this became very tricky. The configuration management system was an in-house product. The monitoring systems were in-house. We have 40 different kinds of hardware to manage, and of course, with a limited budget and a flat budget and limited staff, this stopped us from expanding, and we needed more compute resources, so we needed to manage that better. So we started a project which we called the Agile Infrastructure, because Agile was a good word in those days. And we came up with a few different projects within that structure for monitoring, configuration management, and one was for compute. So we started to actually look at a private cloud solution. We looked at a few different solutions, but already quite soon we realized that OpenStack in 2011 was having a lot of traction. There was a lot of momentum behind it. In those days, of course, it was essentially Nova and Swift, but we could see that there was a lot of industry backing for it, and this we thought was interesting. Because to be able to operate something at our scale, we felt we didn't want to do that alone anymore. So there you go. This is what I was saying. One of our design goals there as well was actually to virtualize our infrastructure. We'd been given, our main batch farms were under our control, but lots of the experiments had their own machines which we were giving, which were hosted in the computer center. We were sort of managing them for them, they were sort of managing themselves, and very often they just got forgotten. Of course, they were also over-dimensioned. Hardware became much more, even commodity hardware became much more powerful in those days. But if they're just running a simple web server, and they needed 30 of those, it became expensive very quickly. So we wanted to virtualize everything that was virtualizable, and that turned out to be way more than 90%. Clouds were coming up, and the experiments that were experimenting with particularly with Amazon in those days. So they were very interested in cloud endpoints. We wanted to offer that as well. We wanted to be able to separate the hardware management from the commissioning layers and to be able to scale horizontally. And as an extra bonus, we were running a virtual infrastructure already, but this was very much focused on server consolidation use case, much less on bare compute. So we wanted our private cloud to consolidate the run classic server virtualization as well as scale out cloud compute. So we turned to OpenStack. Not only to OpenStack, I must say, we turned to lots of different open source projects. We realized actually that that was not only beneficial for us, it was also fun. We started to contribute to these communities. And here we are, going to events like this one and giving away stickers. And it's really enjoyable. It also helps a lot in our hiring, I must say. We very often get students fresh out of university to contribute to our projects for a few years, and nobody of those knew the Quattro management tool suite or the Lemon monitoring framework. They do know Elasticsearch, they do know Puppet, they do know those concepts. So it makes it much easier to onboard newcomers, and it actually also gives them, of course, a valuable experience once they leave us again after a few years. So 5 years of OpenStack in one slide. We started our first pre-production service in 2012, based on a release called Essex, and we've been upgrading that ever since. Not completely true. Actually, it was in summer 2013 that we opened our OpenStack service for production, and we've been upgrading that one ever since. We started with core components, Nova, Glance, Horizon, and Keystone. But you see that we've been adding things and sometimes removing things until we've got quite a catalog of 10, 15, almost 15 different components. The logos you see in the bottom, they denote those components. There's a sticker for somebody who can tell me which ones they are. And I cannot do the check myself, I must say. So for those of you who are not that familiar with OpenStack, you see the 6-monthly release cycle. And we try to stay close to that. Initially, we were upgrading all components on one big bang day. That didn't really work out anymore. So around the time of Havana, we started to break down things. And we actually run all our components on their individual virtual machines, so we can upgrade them in sync. So at the moment, we've got components running Pike, we've got Okata, but we also still have a few things on Newton, actually. So the dates that you see on the top, the orange line there, actually denote the day when we upgrade OpenStack Nova, which is the biggest, most complex and most crucial component for us. When that one goes to the next one, we add another column to this table. This goes fine, by the way. In the earlier days, OpenStack had a bad reputation for not being upgradable. We never really understood that. We found that if we broke down our deployment into the individual components, most of them upgrade just fine. And we've been running, as I said, since 4 years now in production, just upgrading components. It's been pretty smooth compared to the upgrades of some other software that we're running in the computer center. It's been growing in size as well. We are now running some 280,000 cores out of the 5 million that Eldik mentioned earlier. I think it's a fair fraction. I believe there must be more in total in the world. There must be. And you see the steady rise of the number of cores over the last 4 years. And if budget permits, that will continue to grow. I'll say more about that in a bit. So what do we do on this cloud? A lot. Our users are quite demanding, very computer savvy as well, and they come with all sorts of different use cases to us. So our main use case in terms of resources is the batch use case. So the number crunching on the physics data. About 85% of the cores that we've commissioned are used for that purpose. The virtual machines that we give there to the batch team are then run under schedulers like LSF, in particular HT Condor, to bring the workloads to the servers. But we also use them for all the IT services that we run ourselves. Our Puppet infrastructure, our web servers, database servers, all the organizational stuff that you can imagine. The experiments, they run their web servers and their built infrastructure there as well now, so they no longer need these dedicated boxes that were I mentioned earlier. Engineering services we have the hostel booking service there as well. We have the car rental there. We have some of the medical services there as well. And as you can imagine, all these different people consider their services as critical. As you can also imagine, hostel booking and car rental, those are not really cloud-ready applications. Those tend to be rather mature services that expect all sorts of things from the underlying infrastructure. And running that kind of services works for us, but it's pretty interesting as well. We say license servers are a pain, for example. They are not really cloud-ready, but we're running them. And it works. And then we give some, everybody who signs up for our service gets a quota of a few virtual machines to play with. So we have those ones for the personal VMs as well. And there's about 3,000 people who've signed up to the service so far. So it's pretty big. This comes, of course, with all sorts of operational challenges. You heard about the OpenStack Compute Nova service, which has which for us is very important to scale horizontally, and we do that using a feature called cells. That feature has been around for a long time, and we're looking forward to the version 2, which has been coming along for quite a while as well now. Because we need this feature to work very, very well for us, because we need to actually add cells to be able to grow our capacity. It's one of our more technical, interesting challenges. To test the infrastructure, we use a component called Rally. We commission Rally to run hourly tests on all these different Nova cells and all the other parts of the infrastructure. And we report this back in our Grafana and Elasticsearch dashboards. I chose a screenshot with some red in it, but it's more green than red. And usually there's even more green than you see here. One of the more recent additions to our service catalog is a component called Magnum, Container Orchestration as a Service. 2 years ago, all CERN physicists got interested in running containers and container clusters. And some, of course, wanted to run Kubernetes. Others were more interested in Mesos, and later on in DCOS, Docker Swarm, Swarm mode. This was not something that our department could offer support for. Fortunately, OpenStack encapsulates all that into a service called Magnum, which allows people to actually choose the container orchestration engine they want and run that on our infrastructure. So we started to contribute to that some 2 years ago, I think. And we've been running that in production now for a year, and our users are very happy with it, and the uptake has been very good. I'm sure this one will continue in the coming years. What you see there on the right-hand side are the logos of the CERN Open Lab, which is a partnership with industrial partners who actually can test ride either new hardware or new software in the CERN environment, and they sponsor us with fellows. So our Magnum work has been sponsored by Rackspace. We've had a fellow working for us for 2 years on that to make sure it actually works for CERN, and this has been very successful for us as well as for Rackspace. The fellow we hired, we actually get to keep. We offered him a new contract. He's now working for CERN rather than for Rackspace. and he is the project technical lead in OpenStack, of which I'm very proud personally. We are looking at a workflow as a service, a component called Mistral, which is actually very useful for us because we have to make sure, of course, that OpenStack works in the CERN environment. As I said, the environment is 40 years old, so it's not a green field at all. We had to make sure that OpenStack would actually function with our Active Directory infrastructure and with our legacy apps and our very interesting CERN and networking infrastructure. So we need some glue somewhere. And in particular for the management of users, creating new OpenStack accounts and projects, etc. We are looking at a component called Mistral, Workflow as a Service. One interesting thing that we'll be doing soon is actually expire those personal VMs. Because you can imagine if somebody comes along and gets quota for a few VMs, he will boot them and then he'll go do something else and forget about them. There's not really any charging infrastructure, any billing infrastructure at CERN, so we do lose some resources through that sort of cracks. And we're going to be using Mistral to actually plaster over that and actually recuperate services like that. Also in automation, we use a component called RunDeck. I'll be very brief because it's not an OpenStack component, but an open source project that actually allows you to automate some routine operations. And our hardware teams use that to actually take compute nodes out of production, move virtual machines to other compute nodes, do the necessary operations and put them back. So we can write workflows there to complement the things that we're doing with Mistral. Another recent addition, so recent that is not really in production yet, is OpenStack Manila, file share as a service. We've traditionally offered Cinder block storage with Ceph in the background to our end users. But actually file shares are, for many of our users, much more interesting than the pure block storage. So our Ceph team at CERN, who are awesome, by the way, started to offer CephFS by the time that one reached production maturity. And we started to look at Manila on top of that. And that looks all very, very good. We're about to upgrade Ceph to the Luminous release, and then we can actually make Manila file share as a service, a production service, and offer it to our customers. I'll skip this one and that one as well, although they're a lot of fun. Operations is, has been a challenge and keeps being a challenge, and I don't mean challenge in the word of a problem, but really a challenge. We've started with a few racks of servers. We now have 8,500 hypervisors, and we will continue to grow that. So to make sure that we, with our fixed amount of staff, can do that, we have to continue to invest in further automation. One very important area for us is the software-defined networking. I mentioned that the CERN networking environment is very mature, and that is a euphemism for hard to deal with. But we are now setting up a project to actually investigate, can we bring software-defined networking into the CERN data center? Can we start to leverage the advanced features that Neutron offers? And with advanced, I mean things like floating IP addresses. For CERN networking, that's already very interesting. So it'd be great to get rid of some legacy in that domain in the coming years as well. We're also partnering with Weiwei in the Open Lab, excuse me, in the Open Lab context, and we are starting to work on a Nova feature called preemptable VMs. So we are, as I mentioned before, we are not really billing for the services that we provide to the experiments. There's a show-back model rather than a charge-back model, but there is a lot of, if there's idle capacity that nobody's asked for because we've just commissioned something or because the conference is just over, the peak load is gone, there are actually idle resources. And we'd like to use those with very low SLA virtual machines to run Monte Carlo productions or basically run VMs that we, the operators, can shoot down anytime we want. And there's a blueprint for preemptable VMs that would actually allow us to automate that and fill in those gaps in the the provisioned resources. So that's interesting. Nova Cells V2 I touched upon. We've got fellows sponsored by Weiwei to do the developments upstream for that. In fact, that's a very important thing that I should highlight. We've been involved in the OpenStack community since 2011, 2012, but not as consumers, but as contributors. We've been providing code. We've been doing documentation, we've been writing blog posts, we come to events like this. We've had representatives on the board of directors. I mentioned we have a PTL, we've got core reviewers. You will find CERN all over the OpenStack space if you start looking for it. And that's great fun as well. Compute needs will continue to grow. So we are now in a phase of the LHC computing called Run 2, but there's going to be 4 runs in total. And the amount of compute that is estimated to be required for the experiments, it will go up by a factor of 60 in some scenarios with what we have today. The money will not go up by a factor of 60, so it won't. So the experiment software needs to become more efficient. We need to become better at provisioning hardware. We cannot excuse me. We cannot afford to have idle resources. But another thing is we will not be able to host all that equipment in the CERN data centers. So we're starting to look beyond the CERN data center as well, and obviously public clouds could play a major role in there as well. So we started to look at that a couple of years ago. The experiments on their own already dealt with providers like Azure and Amazon. At CERN IT also have been running some projects with commercial cloud providers in Europe, because we're a European organization. And one I want to highlight here was an experience we had last year with the OpenTelecom Cloud. They're there. Where we commissioned 4,000 cores when they started to offer an OpenStack infrastructure, which was a good experience for us as well as for them, because it was very fresh at the time. But what was interesting for us was that we actually extended our CERN batch farm onto public clouds. So the experiments themselves didn't need to bother with anything. These resources for them were completely transparently added to the CERN infrastructure. So we could actually burst into public clouds, and that was a good success. The plot on the left-hand side in the bottom shows you how we varied the workloads of 3 of the 4 experiments by changing the configuration of our batch system. And you could see that we could run that for months at a very high occupancy. So we'll see how that one pans out. We need a lot of more capacity in the coming years. So to summarize for you, because I've overrun already, CERN have been operating a production cloud since 4 years, but OpenStack Cloud since 5 years, and actually we've been involved with OpenStack itself since 6 years. We started out doing bare compute, OpenStack Nova, but then we added block storage, and we continue to add new features like container orchestration engines and file shares as a service. And our customers appreciate that additional functionality very, very much. We've been working with OpenStack. We've been working with OpenStack partners, which is it's been a very good experience for us. It's a different way of working than what we were used to, but not only refreshing, I think it's a superior way of working. We benefit from it a lot in terms of the compute services that we can offer, and also in terms of the experience that we can offer to our temporary staff, who will be with us sometimes for a year, sometimes for 3, but who learn something useful before they go back to industry. And these were just the first 5 years. I hope there's going to be many, many more years. You've seen there's quite some challenges ahead of us, and I'm quite sure that we'll continue to use OpenStack to try to meet those challenges. Thank you.
Thank you so much, Jan. So, any questions for Jan?
Thanks again, Jan. That was very good. Always enjoy your sessions. Saw with interest you retired your Ceilometer project a while ago now.
Yep.
Should I assume you migrated your monitoring across to your hold on, I've lost the name of it. The new monitoring solution you listed in your project list there. Is that your thinking around dropping Ceilometer?
Ceilometer at the time was I'll put this delicately. It looked very interesting for us, so we deployed it initially, but we grew faster than Ceilometer could keep up with. We had problems actually scaling that infrastructure. For us to write the amounts of data that was produced by all the Ceilometer sensors, the infrastructure couldn't keep up with it. And I remember a session in the OpenStack summit where basically the title was, how can we make Ceilometer scale to the CERN needs? It didn't go quickly enough for us. In addition to that, we had a monitoring solution from one of the other projects based on Elasticsearch, Logstash, Kibana, Flume, other open source tools, which was for non-OpenStack monitoring. So there was already a monitoring service being developed beyond our OpenStack needs, and we started to leverage that. So we retired a large part of the Ceilometer infrastructure, but in fact we kept some parts. Nova notifications, for example, still go to Ceilometer, and some other notifications as well. So whenever I show that slide, I just hope nobody asks, why did you cross it out? Because we didn't really cross it out. Well spotted.
But you moved your main monitoring across to Manaska then, did you? Or?
No. We're not using any, for our monitoring, we're not really using any OpenStack components.
Okay.
So.
Cool. Thank you.
Any other questions?
Okay.
Quick question. It sounds like you're doing your upgrades, creating the OpenStack services as pets, running them on systems. Yep. Have you explored running the control plane as containers and benefiting from things like auto-scaling and upgrades with, OpenStack Count? There's a bunch of projects.
Yeah, yes. It's on our to-do list. It's not how can I put it? It's not one of our pressing concerns because we've become so good at upgrading it now. We upgraded Cinder to Pike 2 days ago with a API downtime of 5 minutes. But it's definitely on our to-do list to check that one out. Yeah. Also, because we'd like to, at the moment we're running all those components in virtual machines under OpenStack, but we could visit other deployment models where actually, if possible, we actually containerize that part of the infrastructure. We don't want to be too close to the leading edge of things, though. We can take our time.
Yes, you have a kind of, thank you for the talk first.
You're welcome.
You have a sort of a distributed system where you collect information in some location, you have data centers in different locations as well, and sometimes you rely on the public cloud. Mm-hmm. So I was wondering, and you also said that your networking infrastructure is mature. So I was wondering what actually would be like the overall networking architecture that you have, and what kind of, like, for example, switches you're using, and if you have like triple cross layers of the switches in order to balance the loads. Or if you have something very simple, like just...
We have something actually very simple, but very mature. So top of rack switches, little redundancy, because as I said, 90% or so of the compute infrastructure is used for number crunching. If we don't need a lot of redundancy is that if there's a switch failure, too bad, we'll relaunch the jobs. So for most of the infrastructure, there's very little redundancy. Cheap commodity. That's true for the servers as well as for large parts of the networking infrastructure. It's not very enterprisey, shall we say? So, because we want to keep the costs low.
Okay, one more question over here. So. Right over here.
Hi.
Yes. So during the talk, you've mentioned two similar concepts. First, you talked about expiring user VMs after 6 months. I think using OpenStack Mistral for automating that. And then later on, you mentioned that new OpenStack Nova feature for low SLA VMs. So how they are different on a technical level?
Okay, so these personal VMs are, we don't know what they're doing. They can be used for development purposes. They can be just forgotten. The person can have left the organization, or we cover that case. But it is something that we actually show back to the experiments. Look, your users are using that, right? And they want us to clean this up. We want to clean that up as well. But we are showing that back. The VMs are there. The quota are being used, but they're idle typically. Right? We want to catch that with workflow. The low SLA preemptable VMs, we actually want to use those to fill all the idle resources we have until, so to say, more important workload comes along. So for these ones, we do not guarantee any quota. We will say, look, as long as we've got resources for you, you can launch these preemptable VMs, but as soon as other customers, more important ones, come along, we will shoot them. So that's not really exploration, I would say.
Okay, thanks.
Got time for one more short question if you have any questions.
There's many more stickers. You can pick them up at coffee. Thank you.
Okay, thank you so much, Jan.
Thank you. Oh, thank you.